So good morning, everyone. It is my pleasure today to welcome our two speakers at the webinar session. And today we will be starting with Dr. Émilie Génin. Émilie is currently an associate professor at the Institute of Molecular Science in Bordeaux University in France. She initially studied at the École Normale Supérieure in Paris in order to obtain her PhD. It was on metal catalyzed organic reaction, a PhD which was awarded by the prestigious Sigma Aldrich Prize of the French Chemical Society in 2006. Then she had a postdoctoral internship at the CEA in Saclay, and she started to work at the interface between organic synthesis, luminescent nanomaterials, and biology, in particular on the functionalization of quantum dots with organic molecules to provide nanohybrids for smart targeting of proteins. Since 2007, she's very active in the field of the development of photoactive and fluorescent molecular systems for applications in biology and in material sciences. And today, Emily will be talking on fluorescent hybrid nanoparticles for therapy and sensing of biomolecule. Emily, please, this is your time.
Good morning, everybody, and thank you very much. Thanks for the introduction, and I would like to thank the committee and especially Frédéric for the invitation. It's my pleasure to give you a tour about our research today. So just before dipping into science, let me give you a quick view of our region and maybe give you some ideas for your next summer vacations. So a few hours drive from Bordeaux, you can enjoy Dune du Pilat or nice villages like Saint-Émilion, or also the famous Basque country near the ocean. And Bordeaux is also a very nice place to live. You can, for example, enjoy a walk through the Pont de Pierre or near what we call the Miroir d'Eau. And Bordeaux is famous, and you can enjoy wine directly in the vineyard or visiting the museum Cité du Vin. And closer to science, here you have two photos of our campus and our institute. And this institute gathered 10 research groups with a wide expertise going from organic chemists, theoricists, physical chemistry too. And we are dealing with different research areas spanning nanoscience, green chemistry, surfaces, interfaces, and even organic synthesis and modeling catalysis. And more specifically, my research group, the one I belong to, Chimie Molecular and Materials, I'm interested in focusing on molecular engineering and organic synthesis to functionalize materials and provide organic-inorganic hybrids. And to give you the general view, as Frédéric said, I'm an organic chemist, inorganic synthesis, and I'm interested in the multi-step organic synthesis of targeted molecules that we are using most of the time to functionalize materials or elaborate hybrid materials, often for biological application. And the idea is to design and tune the chemical structure to fit with the requirements of the application, and to also understand the structure properties relationships, more specifically after immobilization. My research is about fluorescent and photoactive molecular systems, so basically involving chromophores. And here you have an overview of the different projects we are dealing with in my group. One first axis focuses on fluorescent capsule, for example, for the detection of neurotransmitters as a collaboration between Bordeaux and Pau University. More recently, in collaboration with Laval, I was also interested in functionalizing gold nanoparticles to provide fluorescent system to study their biodistribution and mucoadhesive properties. And one main other topics is related to functional silane, their synthesis and their use to functionalize surfaces, either planar surfaces or nanoparticles. And I will focus on two of the three corresponding projects today. And more recently, we are turning also our attention on different application fields, such as optical memory, working on the development of photo-switchable surfaces by grafting an organic photo switch like azobenzene or DASA, more recently described as photo switch, and grafting them on planar surfaces. So please let me first tell you more about what we did for providing luminescent titanium dioxide nanoparticles for cancer therapy. Because in this project, the overall goal was to offer better treatments for cancers of the nasopharynx regions. We did this in collaboration with German colleagues. And why? Because in this kind of cancer, removal by surgery is often incomplete, and there is quite a high risk of tumor recurrence due to precancerous cells. So our strategy was to develop a gel of fluorescent photocatalytic nanoparticles based on titanium dioxide as a completion of the tumor therapy. So the idea was to apply the gel on the tumor and to check the suitable distribution thanks to their luminescence by UV visible excitation, and then apply the photocatalytic treatment by UVA excitation. And for that, we were involved in the functionalization of titanium dioxide nanoparticles with organic ligands. And these organic ligands had to bear amine terminal groups at the end to enhance their uptake by cells, and also have a dye in the organic part to visualize the nanoparticles during the therapy. So the different ligands that we synthesize are shown here, and in each, they were synthesized in 3 to 10 steps with quite good yields, and all of them bear silylated, triethoxysilylated anchoring groups to graft onto the titanium surfaces. Then we put a linker, including a small PEG unit to help for the solubility and further application. And on the other side, we used two-branch dendron terminated by amine protected with phthalimide groups, and this dendritic structure help us to increase the number of terminal function per anchoring group in order to best preserve at the end the photocatalytic properties. To introduce the fluorescent moiety, we used something like a T connector with this lysine part, and we also synthesize a linear analog of the fluorescent ligand as a proof of concept, and also because it was easier to synthesize and easier to go further with the applications. In terms of synthesis, we started with this lysine group, monoprotected. We did the protection of the amine, and then we were able to perform the peptidic coupling to put the linker, and then deprotect the amine to go further with Michael addition to build the dendritic part, and the other reagents This one with the acrylate and the amine protected was obtained in 2 steps starting from these reagents. Going further, we were able to deprotect this amine and then react it with a rhodamine reagent activated to go through peptidic coupling. And this molecule, intermediate molecule, was deprotected to get the free amine. And as a final step, we were introducing the anchoring group, silylated head group, by reacting this isocyanate with the amine to provide this urea linker. Then, having in hand the ligands, we went further with the easiest one, the linear analog, the fluorescent first, and we grafted on the surfaces of titanium dioxide nanoparticle using classical protocol from the lab. And to prove the functionalization and understand the functionalization of the surface, first we did zeta potential measurement, and the change in the electric potential is a proof of changes onto the surface. Infrared experiments were also very valuable for us because here you can see the spectrum of the organic port, the organic ligand, and in red you have the pristine nanoparticles. In blue, that's the infrared of the hybrid system, and as you can see, all characteristic bands of the organic ligand are clearly visible, proving the functionalization. And finally, the pristine nanoparticles are not fluorescent and white, and the hybrid system is colored as expected and fluorescent, which is very important for us. Going further to study the photocatalytic performances, we were able to show that our hybrid system is even more efficient than unmodified nanoparticles and commercially ones, thanks to a synergic effect between the fluorophore and the titanium dioxide port. And experiment with cells have shown that the system is internalized into cells and biocompatible. So all these results were proven, the proof of concept and the potential use of the system for the cancer therapy. And now let me give you a quick look on another strategy to functionalize nanoparticles, this one magnetic one, and also fluorogenic for detection and sensing for diagnostic application. So on this second project, we were interested in carbohydrates because there are key molecules in a lot of biological processes, and it's known that abnormal blood glucose levels is involved in diabetes, and abnormal glycosylation is involved in autoimmune or neurodegenerative diseases or even cancer. And that's why currently there is quite active research field on the molecular recognition of carbohydrates, their detection, immobilization towards therapeutic or diagnostic applications. And in this context, boronic acid are interesting molecules because they can reversibly and covalently bond with diol, and more specifically with the sugar. So thanks to this reaction, boronic acid are very good candidates as sensor of carbohydrates. And in the literature, there is already a lot of fluorogenic boronic acid. We were used to detect sugars in solution, and we were focusing more specifically on these 3 structures. The first one based on an anthracene, something like an off-on system, meaning that the fluorescence increase when sugar is added. And these 2 isomers of naphthalene derivative, depending on the position of the substituent, one is a ratiometric system, which means that on one part of the spectrum, the fluorescence decrease, the other part, the fluorescence increase when fructose, for example, is added. And the other one, also an off-on system with an increase of fluorescence upon addition of the sugar. In parallel, in the literature, we can find several examples of non-fluorescent boronic acid immobilized on materials for the capture of carbohydrates. Different materials have been investigated, such as polymers and surface modifications, such as gold surfaces, also nanomaterials, several based on carbon, like graphene nanosheets or carbon nanotubes, also gold nanoparticles. And on the right part here, I just wanted to show you two ways of functionalizing the system. For example, the first one involved an amino boronic acid to react with nano quantum dots functionalized with carboxylic group at the surface and going through peptidic coupling. Authors were able to provide a system selective and sensitive for glucose detection. Another way is to start with amine-terminated nanoparticles and to do a reductive amination with an aldehyde on the boronic acid to provide system here, for example, for N-glycopeptide detection. And in this context, the originality of our approach is to develop a system combining the two processes, the fluorescence detection and the immobilization on the materials. And we wanted to develop fluorescent boron-based magnetic nanoparticles for this sugar detection, because magnetic nanoparticles are an interesting system to recycle the materials and separate the material on simply by magnetic separation. And it's easy, fast, cheap, and efficient. And for that, we have shown that the best strategy was to functionalize magnetic nanoparticles coated with silica, functionalized with a coupling agent to provide, for example, amine or aldehyde terminated function, and then post-functionalize the system with a boronic acid bearing the complementary function. In terms of synthesis, the first family of chromophores, the anthracene one, was very efficiently synthesized as a straightforward route with only three steps and an excellent overall yield, thanks to reductive amination, alkylation, and deprotection sequence. Regarding the other family with the naphthalene derivative, we were also able to implement different synthetic routes to provide the targeted molecules in 7 steps with a good yield on the overall synthetic route, because that's more than 70% per step and even more than 80% per step in with this system with the substituent one on each aromatic ring. And for that, the key steps were providing a key intermediate, a common syntone in 2 steps, and then implement different borylation strategy depending of the position of the 2 substituents. And the last important point of the synthesis was to be able to provide pure and stable compound, not so easy with boronic acid. And for that, we went through a strategy involving using a protected boron compound for the borylation, then interconversion in trifluoroborate salt, and then deprotection to provide the boronic acid with very good yields. Once we got the chromophore, graftable chromophore, we worked on the functionalization of the materials. And as I mentioned previously, we used protocols from the lab to provide this kind of materials with aldehyde active function. We are able to quantify the quantity of function thanks to test reaction with densylhydrazine and spectroscopy measurements. And once again, we use infrared spectroscopy to compare the two spectra, the one of the pristine nanoparticles and the one of the hybrid. And as you can see, we have the characteristic bands proving the functionalization. After we did the post-functionalization and by reductive amination, and infrared confirms that we got the targeted system. To go further on the characterization and proving that the boronic acid was effectively present on the system, we did experiment with transmission electronic microscopy. And here you can see the different nanoparticles with the organic ligand surrounding it. And to go further in the analysis, we also did microscopy with coupled to X-ray spectroscopy to map the different atoms. And here, with the carbon-oxygen silicium thing, you can clearly see the inorganic parts, the magnetic nanoparticles. And then, if you check with the carbon and only iron, you can see that carbon, so the organic part, the organic ligand, is functionalizing the magnetic nanoparticles. And we also did some fluorescent microscopy experiment to here you have the images with a classical microscope, here with the fluorescence analysis. And when you merge the two of them, we were able to prove that the fluorescent boronic acid is in fact graft to the system. The next step was to test the reactivity of the systems for the detection of sugar. And here you have the example of the anthracene system with addition of fructose. And as expected, we have an increase of the fluorescence. We did this for several sugars, 3 of them, as well as sorbitol. And we were able to draw curves with the comparison of the intensity compared to the initial intensity. So here you can see the increase. And the important thing is we have a significant increase. So the detection is working. And that's even in this case is better than in solution. We were also able to calculate the association constants. And here you can see that the affinity is higher for fructose than galactose and glucose, which is the classical order observed in solution. In terms of limits of detection, they are in between 0.8 and 3.7 millimolar, which is relevant regarding the concentration for diabetes or even healthy patients. For the other system, the off-on naphthalene system, we did the same. We once again observe the increase in intensity. And here you can see the different curves. And we have still a significant increase in the fluorescence. Interesting, quite similar with the solution. And in this case, there is interesting changes in the selectivity because the glucose has a higher affinity, for example, than the galactose, and limits of detection are still interesting. The ozonaphthalene system with the ratiometric behavior is also working. Here, same thing with fructose, we have the increase of intensity. and we have good enhancements of the intensity upon sugar addition. And this time, glucose is has the highest association constant compared to fructose and galactose. So it means that depending of the system, the selectivity is tuned due to the arrangement around the nanoparticle and due to the initial system himself, still working with the increase of intensity. The last thing for us was to test the possibility to recycle the system thanks to the magnetic properties. And so we did a first run here, and then we did the separation, by the magnetic separations. We remove the solution, put a new aqueous solution, and went again for a second and a third run. And as you can see, the 3 cycles are almost the same, so the system is stable and we can recycle, and the system is still active. And one important thing is that we do not have to have extra steps and a protocol to remove the sugar. We have the decomplexation of the sugar, which is spontaneous when we change the solution and put a new one. So just let me now thank all my collaborators and the students who were involved in this work, and my collaborators from Germany, and all the financial support who provide us fundings to go through this research, and you for your attention. Thank you very much.
Thank you very much, Emily, for this great presentation. It's very interesting always to see what you're doing in your lab and with these very interesting results. It is time for a few questions. If you have, you can either raise your hand or start speaking, please. Anyone? So I will start with a question on your on the last part of your talk, Emily, with this great system to detect the saccharides, and I'm not sure I really understood how do you decomplex them at the end after separation.
And the interesting point, and probably surprising also, is that in literature, most of the time, the complexation is quite strong, and you have to change the pH to induce the decomplexation. Here we got this, let's say, unexpected but also interesting result, is that it seems that the way the chromophore are arranging on the nanoparticles involved spontaneous decomplexation when we put the system in a solution without sugar, meaning something like equilibrium displacements. And if there is no sugar, the sugar can decomplex spontaneously, and we can get back the system and go back for sugar detection, sensitive to the increase of concentration. But if you remove the sugar complex on the nanoparticle is also basically going out.
Nice, thank you. And how in a real device, how would you use the particles? Because they are
for the moment, I would say that it would be an external. I think what we are targeting is an external system based on blood samples or other samples from patients, and doing the process in something like in cuvette or in a system outside the system. Inside, I think it could be possible, but maybe also the interesting point for us was to prove that the system can work and after we have in mind to maybe change also the support depending of the application. I'm not sure that these quite big magnetic nanoparticles are the best system to go something like in cellular or other things. Here the magnetic part is also for the recycling of the system.
Thank you. Yeah, that's very neat. It's really nice.
Thank you very much, Frédéric.
Emily, you did not observe any aggregation of the nanoparticles depending on the sugar moiety?
We don't think that we have this kind of problems, but probably also because the nanoparticles are quite big compared to the system, the functionalized system. But I quite agree that it was a kind of thing we were wondering, and I think still need to go deeper into it and to better understand what kind of structural properties relationship we could have, because I agree, as there is a lot of active sites, it could happen. But for the moment, not so much observation.
Nice. Thank you,
Perfect.
Emily.
Thank you very much to both of you.
Do we have a other question from the audience for Emily? So if not, then we can.
I will just ask a
Sorry.
question very rapid. Concerning the first part, you would like to irradiate with UVA 365 nanometers. Are there some systems such as endoscopes which could deliver this kind of light?
Honestly, for that, I'm not sure. The idea was that as it was in the mouse, that's easy to access. So the kind of concept we were targeting, we did not have to consider this kind of thing. I think I'm not an expert on that, but I don't think it would be suitable if you need endoscopy and things like this. And the point after is to tune the wavelengths probably, but to change the system, because for titanium dioxide, that's UVA, which is active. And you see with the rhodamine port, with the synergic, let's say, effect, that's because with the rhodamine, you can absorb light in the red part and after transfer to the system, so you increase the window where you can absorb. So.
Perfect.
Thank you.
Thank you.
Thanks a lot.
Thank you very much.
We can thank Emily again for her great presentation. So this is a virtual applauding. Thank you very much, Emily.
Thank you.
And then we will move to the next presentation. And it is my pleasure today to welcome Salim Oak. Salim, you can also share your presentation if you like now. And so Salim is an associate research scientist at the Petroleum Research Center at Kuwait Institute for Scientific Research, where he supervises the spectroscopy laboratory since 2016. Salim actually had his PhD from the Technical University of Dresden in 2008. He was working on the comparison between high resolution solid state NMR, high temperature NMR in the melt, and high pressure solution NMR in supercritical carbon dioxide in order to investigate fluoropolymers. Then Salim conducted his postdoctoral research in several institutes, including the School of Earth Science in Ohio State University, the Max Planck Institute for Microstructure Physics in Halle, and the Chemistry Institute of New Materials at Osnabrück University. This is where he studied the dynamics of polymers confined in order to order nanoporous alumina membranes and confined fluids. Through his career, Salim has been an active principal investigator and task leader on several research projects, international and national projects, that have allowed him to explore a great range of fields, which includes polymer thin films, natural edible oil, petroleum chemistry, asphaltene science, vegan food, nanoporous engineered proxies, confined fluid inside nanoporous matrices, and polymeric fibers prepared by electrospinning. He has been also awarded with prestigious grants and fundings on national and international collaborative projects. And all this great experience for many years has resulted in the publication of 45 peer-reviewed articles. Salim, please, this is your time.
Can you, first of all, let me say good morning and good afternoon at the same time. Can you see my presentation?
Not sure we can see your presentation. We see something, but this is probably your screen, but not your presentation.
Can you see
Yes.
my presentation now?
No, we can see ourselves. We can see the Google Chrome page.
Um, okay, well, because on Safari it was possible, but on Google Chrome I think there is a little bit problem. Okay.
No, we see repeatedly ourselves.
Yeah.
The- yeah, the browser does not affect the sharing of the screen. Maybe can you try going on PowerPoint?
Yeah, just a minute, please. So now I'm on PowerPoint.
Mm-mm.
No, we cannot see it. Maybe do you have two screens?
Oh yeah, just a minute. Maybe.
Okay.
No, I don't have two screens. Okay, I'll just shut down the Google Chrome and switch to Safari. Maybe it's gonna be
Okay.
better.
Okay.
Okay. Okay, we wait a few minutes. Okay. Hello again, Salim.
Hi again. Now I'm presenting my screen.
We can see your screen with the Safari window open. And
Yes.
now we can see PowerPoint.
Okay, now you can see my PowerPoint.
Yes.
We do. Thank you.
Excellent. Thank you.
Yeah, so I'll continue with Safari. Sorry, maybe there's a problem with the Google Chrome. I don't know.
Okay.
So, yeah, first of all, let me say good morning and good afternoon to all of you once more. Today, I will present some of our recent research efforts about asphaltenes. The title of my talk is From Submolecular Level Structural Elucidation to Obtaining Nanoporous Cross-Linked and Activated Carbon Networks. So we convert problematic asphaltenes in petroleum industry into a potential useful product. Thank you again for the nice introduction. Actually, I have been, since the last 7 years of my life, I have been working at Petroleum Research Center of Kuwait Institute for Scientific Research. At the beginning, let me just mention that we have several contributors to this study. Dr. Jacob Samuel, Mr. Suhaib Kholusi and Mike Fernandez from our center, and Dr. Mohammed Enes Hijazi and Dr. Levent Trabzon from Istanbul Technical University in Turkey. Kuwait Institute for Scientific Research, shortly well known as KISIR in the region and in the world, has been established in 1967. And today, KISIR is a home to over 580 researchers. We have around maybe over 100 laboratories, and we are located at 9 different places. We have 4 research centers, and as I said, I have been working at Petroleum Research Center, and we have also Water Research Center, Environment and Life Sciences, and Energy and Building. We're located somewhere here in Ahmedi, and at our Petroleum Research Center, we work on different topics such as corrosion assessment, improved oil recovery, optimization of petroleum refinery, polymeric products, and refining capacity expansion and flexibility. At the beginning of my talk, I just like to introduce you the major motivation factor behind this study. Crude oils, or a typical petroleum, contains thousands and or maybe 10,000s or even more number of molecules. So in other words, crude are complicated mixtures, but while defining this complicated mixtures, we can classify them into four different components, which are saturates, aromatics, resins, and asphaltenes, and shortly we call them SADA. Among those four fractions, our focus is on asphaltenes. Why? Because asphaltenes are so much problematic. I just like to show you one example here. For example, asphaltene molecules can form aggregates and then they can block the pipelines. They're also problematic during transportation. They're problematic in refining process. They might deactivate the catalyst materials. And the other thing is, on the other hand, we classify crude oils as three different types of crude oils. One of them is light crude oil, the other one is medium heavy crude oil, and the last one is heavy crude oil. In addition to this, recently there are some efforts where people started using asphaltenes as a raw material for generating new materials. For example, carbon fibers, for example, in battery research, and also some people started using them or testing them as filler materials for polymer composites. And in the current study, at first we focused on structural elucidation of asphaltenes. According to literature, there are three different types of models concerning asphaltenes because it's really difficult to have a clear-cut definition of the chemical structure of asphaltenes. The first model is called island model or modified Yen-Mullins model, where we have some aromatic cores and then the alkyl chains. And the other second popular model is called archipelago model, where we can have the aromatic cores bonded to each other via certain alkyl bridges. And recently, some researchers, they added one more model, which is called our link core model, where we might have such aromatic species, especially bonded to the central core via just one bond. And asphaltenes are considered as cost-effective materials in different fields. They could be fillers in polymer composites, or they could be used as sorbents for separation techniques. And we could also consider them as a precursor to synthesizing novel carbon-based nanomaterials. In the current study, we worked with five different types of asphaltenes derived from either heavy crude oil, medium heavy, or light crude oils. Actually, there are certain ways to define the borders for light, medium heavy, or heavy crude oils. I don't like to go into deep details, but American Petroleum Institute, which is shortly known as API, has put certain way of defining those crude oils. And for example, in the current study, we started with such crude oils such as sample 2 is a heavy crude oil, sample 3 is a heavy crude oil, but on the other hand, samples 4 and 5, they're light crude oils. Especially the crude oils with API gravity value higher than 28.4 are considered as light crude oils. Between, for example, 14 and 28, they are considered as medium heavy. And lower than 14 API gravity, we define them as heavy crude oils. In the current study, first we followed a very standard procedure to extract asphaltenes from crude oils. So we take crude oils and then we put them, and then we take heptane and we pour heptane into crude oils to precipitate asphaltene molecules. As I said, there is no clear-cut definition for asphaltenes, but the solubility is the definition is based on solubility. So asphaltenes are such molecules which are insoluble in heptane or pentane type linear alkanes on the one hand, and on the other hand, they're soluble in benzene and its derivative toluene and chloroform type solvents. After overnight treatment, we use filter paper and the maltines, they just go through the filter paper, and the precipitated heptanes the precipitated asphaltenes in heptane, they just stay on the filter paper. Later on, asphaltenes are extracted using toluene and Soxhlet extraction at 60 degrees Celsius, and ultimately we just dry our sample at 80 degrees Celsius in an oven, and we obtain our asphaltene samples. The first measurements that we conducted on our samples are NMR spectroscopy measurements. Let me just remind you about NMR. To do NMR first, we need to have external magnetic field, and we need to have the samples. But with those two only, we cannot do, and we need to excite the spins by radio frequency fields. And when we do NMR, at first we obtain time domain data, and when we do Fourier transform, we end up with the NMR spectrum, so the frequency domain data. This pulse sequence here, we call it free induction decay, shortly FID or NMR signal. And as I said, when we do the Fourier transformation, we can end up with the NMR spectrum, the frequency domain data. Here's a simple example coming from ethanol, and we can also easily assign the function groups to the resonances to certain function groups such as CH3 or CH2NOH. However, in real life, of course, we do face much more complex problems such as asphaltenes, and we need to work with modified pulse sequences, and we need to go to advanced NMR techniques to focus on the complicated or complex problems. For instance, when we consider proton NMR or carbon-13 NMR of asphaltene samples, as you can see here, the resolution is not very good. We cannot gain a lot of information. All we can say, okay, between 0 and 2, they are all aliphatics, and between 2 and 4, they are all cyclic alkanes, and around 6.5 and 7.5, which is fine, but we just observe aromatic protons. Therefore, two-dimensional NMR spectroscopy needed, and when we focus on the same problem with advanced NMR techniques, we recognize that we gain much more information. For instance, we applied Toxi NMR, which is giving us information about both, let's say, through bond and through space type interactions and homonuclear interactions between different protons, or when we apply HSQC, which is well known as a two-dimensional heteronuclear NMR experiment, or HMBC, another heteronuclear NMR experiment. As you can see, when we switch from one sample to the other, and when we just zoom into the same region, well, we can see also differences. For example, here, or for example, those correlations, they don't exist here in the spectrum of the sample 2, and so on. And when we conducted HMBC experiments, we gained even further information, because HMBC also tells us information about the longer range distance interactions between different protons and carbon-13. And at the end, what we did, we prepared a list of the correlations that we observed. Maybe it's 20 pages long, but I just like to show you an example. For instance, we observed different correlations between protons and certain carbons, like triaromatic carbanoid or diaromatic carbon, and then diaromatic carbon with ring junction carbon, like fluor type structure, as could be seen here, or it could be also Bay type carbons, as indicated here. And ultimately, we also observed, for example, traces of porphyrin structures, which are shown with the minus ppm values in carbon-13 NMR spectrum. And we are also able to observe some, let's say, organic salts as well. And of course, when we look at such tables, which are also pretty long, they are so much boring. That's why what we do, actually, we convert them, of course, by referring to literature as well, we convert them into certain hypothetical structures. For instance, in the case of asphaltenes extracted from heavy crude oil, we're able to observe such interesting structures and also such functional groups, as you can see here. Plus, when it comes to porphyrin structures, we think that there are also some heavy metals such as nickel 2+ ions in the structure of the porphyrins. And when we switch to the asphaltenes extracted from light crude oil, again, there are similarities, but at the end, for example, we didn't observe the traces of heavy metals. And on the other hand, we are also able to observe some sulfur species. So advanced two-dimensional NMR spectroscopy allowed us to talk about the submolecular characterization and clarification of the certain function groups in the hypothetical structures of asphaltenes, and which motivated us to do some further experiments. But at the same time, we were pretty lucky because our review article on NMR spectroscopy analysis of asphaltenes became a cover page in Energy and Fuels, and which also motivated us to do further work. For example, when we compare AFM images coming from literature and the hypothetical structures that we proposed by NMR spectroscopy, there are very nice similarities. Just imagine those two works published in two different years, and where the asphaltenes, they come from completely different resources. As you can see here, we see a central core in our hypothetical structure, and here as well in the AFM image. And you can also see the tail structure with the aromatic and cyclic alkanes here and here as well. Plus, like there's another example. As you can see, again, we observe a central core here, which is also existing in our proposed hypothetical structure. And there are also so many, as you can see here, going down and going down here, so many similarities between what has been imaged and what we proposed in our work. And those functional groups, they really motivated us to do further work because they might ease our work, especially when it comes to potential reactivity. So then we focused on modification of asphaltenes. What we did is that we worked in chloroform, which is one of the solvents for asphaltenes, and we also worked with iron chloride, which is a catalyst material in this case. So asphaltenes and asphaltene aggregates, as I said, they're problematic, but we benefit from this attitude of asphaltene molecules, and we end up with polyasphaltenes. That's why we consider the asphaltenes, let's say, natural products, but showing polymeric behaviors, both in solution by forming aggregates and also as cross-linked materials, which is also a pretty straightforward reaction at room temperature. Then, to characterize those samples, we conducted several different experiments. For example, we focused on, first of all, determination of the surface area of those cross-linked materials. And we recognized that the surface area is between 90 and 151 meters square per gram. In addition to this, when we applied non-local density functional theory, we were able to talk about maximum pore size between 1 to 2 nanometer, which is also pretty nice. And later on, as you can see here, we made a very simple visual inspection test. And for example, we use the chloroform and toluene, which are the solvents, for raw asphaltenes. But when we switch to cross-linked asphaltenes, they are not soluble anymore. So right now we are happy that we are able to obtain such a new material. Because we checked the literature before we start this work, and we recognized there was only one patent dating back to 1965. And again, this study also became a cover page story. And the nice story is that we submitted our manuscript on Thursday afternoon, and Saturday, the editor was so happy. And he accepted the paper, but of course, it still went to reviewers. And getting such nice results motivated us to do further work. We checked the literature and we recognized that maybe we can also focus on carbonization of those asphaltenes to obtain porous activated carbon. And we recognize that there are so many contributions, but mainly coming from, for example, fruit peel type materials, raw materials. However, in that case, for example, people are talking about certain fruit peels coming from very far distance countries, but on the other hand, asphaltenes, they're always readily available for any people who like to work with asphaltenes. That's the first basic advantage. And second advantage is that The carbonization is pretty straightforward. So what we did is that we started with mixing our asphaltene samples with potassium hydroxide. And after that, we treated them at 600, 700, and 800 degrees Celsius, of course, under nitrogen flow. And ultimately, we purified our samples with 1 molar HCl, and we washed them again with deionized water. And after drying under vacuum for 24 hours at 120 degrees Celsius, we ended up with our, let's say, porous activated carbon materials. As you can see here, compared to raw asphaltene, thermally speaking, the carbonized asphaltenes are pretty stable. That's the first good news for us. And second, when we focus on the porosity of the carbonized materials, as you can see here and here, the carbonized asphaltenes, they show a pretty nice porosity. And in addition to such characterizations, we also focused on the characterization of carbonized asphaltenes by spectroscopy, especially when we refer to Raman spectroscopy. We recognize Raman spectroscopy of asphaltenes. We recognize that asphaltenes are derivatives to graphene. So when we do the thermal treatment, as you can see, from raw parent asphaltene to the thermally treated ones, there is a shift, which is fine in different bands of the Raman spectra. But at the same time, we recognize that the carbonization of the asphaltenes resulted in graphene oxide type structures, and even partially graphene oxide type structures. And when we monitored the carbonization by X2 drift spectroscopy, which is diffuse reflectance infrared Fourier transform spectroscopy, as you can see here, there is a reduction in the symmetric CH2 stretching and CH2 asymmetric stretching, which is a very nice indication of the carbonization. And at the same time, there is an increase in the OH peak, as you can see here. And of course, again, we focused on the surface area measurements, and we recognized that the BE2 surface areas of those carbonized asphaltenes, they range from 2,600 up to 3,000, which is a very nice result for us. And again, as in the case of cross-linked asphaltenes, we're able to observe pores down to 1 to 2 nanometer by the NL-DFT approach. Then we started thinking about potential applications, because up to now, okay, we have been doing characterizing the asphaltenes, which is fine. And then in addition to the characterization, we have been also working on, let's say, modification and carbonization of the asphaltenes. But right now we started thinking about the potential applications. One of them is that hydrogen adsorption. And we recognize that the porous carbon structures, they show hydrogen storage capacity of 2.85 weight percent at 1 bar. Besides that, we also talk about isosteric heat of hydrogen adsorption, ranging from 7.29 to 7.55 kilojoule per mole. And okay, there was a slight decrease at high coverage, but on the other hand, we also focused on carbon dioxide uptake or carbon dioxide adsorption. And again, as you can see here, especially in the case of the carbonized asphaltenes at 700 degrees Celsius and 800 degrees Celsius, you can see carbon dioxide uptake in terms of weight percentage up to 26 or 28. Let's say at 1.1 bar, but when we go to slightly higher temperatures, then this carbon dioxide uptake, it started decreasing down. But still, we got pretty nice, promising results. And when we compare our results with respect to values mentioned in the literature, first of all, as you can see here, we have certain natural, let's say, carbonized samples, but coming from natural resources like date sheet or water chestnut type materials. And as you can see here, our surface area is able to reach the values, or sometimes even higher surface area values than the ones mentioned in the literature, even like, let's say, better or higher surface area values than commercially available polymers on the one hand. And on the other hand, when it comes to carbon dioxide uptake in terms of millimole per gram at 0 degrees Celsius, again, our values are pretty promising and closer to the commercial polymers and seriously higher than the other carbonized materials coming from the natural resources. And again, we were pretty happy. It took us, in this case, it took us slightly a year to get our works published in the case of carbonized asphaltenes. But again, our results became a supplementary cover page in Industrial and Engineering Chemistry Research Journal published by the American Chemical Society. Today, just around 1 hour or 1.5 hours ago, we got a pretty nice, we got a pretty nice good news that our work about the gas sensing ability of asphaltenes is accepted by one of the ACS journals. And I just like to, before coming to the conclusions, and let me share this result as well. So our colleagues at Istanbul Technical University, Dr. Levent Trabzon and his PhD student, Dr. Muhammed Enes Hijazi, they work with raw asphaltenes that we provided, and also the cross-linked asphaltenes that we prepared here with Dr. Jacob. And interestingly, as you can see here, the black dots here, they are the data coming from the graphene oxide. And when we switch from raw asphaltenes to cross-linked asphaltenes, as you can see here, the gas sensing ability or sensing performance of different asphaltene samples, they are increasing when we switch from, as I said, raw asphaltenes to cross-linked asphaltenes, or in other words, modified asphaltenes. And it was a pretty nice result. The gas sensing ability of asphaltenes, especially for certain molecules such as ethanol and isopropanol, was shown pretty successfully. The other thing is that, as you can see here, it was sample 3 that has been able to show the highest, let's say, gas sensing ability. And more interestingly, we did some swelling behavior analysis of those cross-linked asphaltene samples by ghost solvent NMR measurements. What do we mean by ghost solvent is that in the case of high-field NMR spectroscopy, we know that we work with deuterated solvents, which is pretty nice on the one hand. But on the other hand, when it comes to, for example, low-field NMR, if we still work with deuterated solvents, then we're not able to get any signal from the deuterated solvents. It's very, very, very weak. So that means when we dissolve our asphaltene samples, or when we place our cross-linked asphaltene samples into deuterated solvents, we are not able to get any signal from the deuterated solvent, and rather all the signal that we are getting, it's coming from our samples. So that allowed us to focus on swelling behavior of the cross-linked asphaltenes, and more interestingly, sample 3, when we compare all the samples here, sample 3 was able to show higher swelling behavior, and more interestingly, the same sample with the highest swelling behavior, the cross-linked sample 3 with the highest swelling behavior, as you can see here, actually is able to show the highest sensing ability towards the ethanol and isopropanol molecules. So there is a pretty nice correlation between the swelling behavior of those cross-linked modified asphaltenes and their sensing behavior. So let me come to my conclusions. First of all, activated porous carbons synthesized from low-cost asphaltenes by carbonization activation pretty successfully. TJ results showed the carbonized samples become thermally more stable compared to raw asphaltenes. We can see the high porosity of carbonized asphaltenes by ACM imaging, and also by BE to surface area analysis. We can talk about surface area between 2,600 and 3,000 meters square per gram. And those carbonized asphaltenes, porous activated carbonized asphaltenes, they are also able to show hydrogen storage capacity and carbon dioxide uptake, which is also a pretty promising result. Besides that, as I told you, those asphaltene samples, they contain sulfur and in detectable range. So that especially in the carbonized nanoporous materials as well. So that means the current carbonized asphaltenes, they could be pretty good proxies for other applications in microelectronics or in solid state batteries as well. Remember, I said there is no clear cut definition of asphaltenes when it comes to their structural elucidation. That's why their definition is based on solubility. And right now, we like to add one more definition to the area of asphaltenes, and which is asphaltenes are such natural and graphene type oligomeric and polymeric materials showing pretty nice, promising features for potential applications. So that's the end of my talk. I like to say my thanks to Kuwait Institute for Scientific Research for the financial support of this study at the beginning, and still we get pretty nice funding from KISIR. And of course, I'm willing to say my thanks to all of you for your patience during my talk. Thanks a lot. And yeah, I'm ready to listen to your potential questions. No, your voice. Sorry.
Excuse me. Yeah, I was
Yeah, sorry.
thanking you for this great presentation. It was very interesting to see this complete story from underground to potentially very highly valuable material application. It's very nice. So we have a few minutes for question. Please. Yes, Emily?
Thank you. Thank you for your talk. My question
Okay.
is about the first part of your talk. I was wondering about using maybe mass spectroscopy to help with the NMR analysis, or maybe confirm some part of your hypothetical your structure.
Yeah,
I was
thank
wondering if you tried, or how do you think?
Well,
What do you
actually,
think?
thank you very much for this point. We already sent some samples, both raw asphaltenes and cross-linked asphaltenes, to our colleagues at University of Rostock. There is a group which is very active on asphaltene analysis by mass spectrometry. So we can validate our results later on.
Okay, thank you.
You're welcome.
Oran, you have a question?
Thank you, Professor, for the talk. And my question is the temperature. What is the role of temperature here? And did you compare the NMR before and after thermal treatment? I wonder what is the structural change, because it's really interesting. At this temperature, there is no deformation or...
Well, that's a very good point. Thank you very much. Actually, your question is about thermal part, whether we did any NMR after the thermal treatment.
Yes.
Yes, we did we did NMR, but low field NMR measurements on the thermally treated carbonized asphaltenes. They're not soluble anymore after carbonization.
They are not soluble. Mm-hmm.
Yeah. Second, considering the effect of thermal treatment, well, you might consider it's like a pyrolysis, because as I showed you during my presentation, there are some alkyl chains as well. So thermal treatment helps with removing all of those. And then we can talk about condensation of the aromatic cores, forming the carbonized asphaltenes. Okay.
Okay.
So that's why it's needed to go to high temperatures, but we need to be careful as well, because that's why we work with nitrogen flow. Otherwise, we will burn and we will end up just charcoal.
Okay. Thank you.
You're welcome.
Do we have other question from the audience? Please start speaking or just raise your hand. Okay, I have a question myself on because it's a curiosity. You mentioned the swelling behavior of the activated carbons that you have. I was wondering, because I'm not very familiar with activated carbons, if it's a common property, and if you have had a chance to compare it to other swelling materials.
Oh yeah, That's a very good question. Actually, let me clarify one little point. Yes, we did. We focused on swelling behavior of both cross-linked asphaltenes and carbonized asphaltenes separately, because cross-linked asphaltene is one type of material, carbonized asphaltene another type of material. But for sure, in both cases, we focused on swelling behavior of those two materials. That's the first point. Second, actually, I didn't compare the swelling behavior of those, especially cross-linked asphaltenes, to any other material. But yes, we are on the way to start an interesting work. Especially, we like to confine simple molecules like water, and then we like to see whether there could be any exchange, for example, between water molecules and D2O. Then, for example, imagine we first confine water molecules into the cross-linked asphaltenes. Then, of course, the NMR relaxation will be pretty short. But when we can exchange D2O with H2O molecules, then, of course, the H2O molecules will become free, independent of the confined state. And they should show, let's say, faster relaxation behavior. And, of course, D2O, we don't worry about D2O in the case of low field NMR because we don't detect it. It's very small amount.
Okay.
Yeah.
Thank you.
But yeah, thank you very much for that point. Especially, we can also compare them with, for example, hydrogels or maybe such cross-linked polymeric materials. Why not?
Yeah, you have. This is a very important field, and we are. Yeah, the story is not. This is the beginning of a new story.
Yeah, exactly. Yeah, thank you very much for listening.
Thank you very much. So I think it is. If we have no more questions, then we can thank Salim again and
pleasure.
Emily as well, our two speakers of this webinar session. Thank you all for your participation. Thank you, Emily. Thank you, Salim. And
yeah, you're welcome. My
wish
pleasure.
you a great day.
Yeah. Please, Happy New Year to all of you.
Yeah.
Thank you. Yes.
Very much.
Enjoy your break. Take care. Bye-bye.
Bye.
Thank you. Bye-bye.